All right, thank you all for joining. My name is Twyla Neely-Strite. I'm a staff person at Illinois Green Alliance. Thank you all for joining us today. I'm going to pass it off to Ben Bartel from our Programs Committee to introduce today's webinar.
Thanks, Twyla. Hello, everyone. Welcome to today's webinar, Aligning Envelope Performance with Optimal Material Life Cycles. My name is Ben Bartel, and I'm a principal engineer with National Property Consulting Group. I want to thank everyone for joining us today to take a deep dive into building facade materials and their life cycle costs. Today's program was produced by the Illinois Green Alliance Programs Committee, a volunteer group that leads the selection, development, and implementation of Illinois Green's education events. The team that organized today's event include myself and Dylan Pranger, assistant professor at IIT. Our audience has been muted upon entry. We will have a Q&A session at the end of this program, so feel free to type your questions into the Q&A function at the bottom of your screen or upvote others' questions, and we will do our best to address them at the end of today's presentation. For those of you, who are joining us for the first time, Illinois Green Alliance is a membership-driven nonprofit that advances sustainability in the built environment to ensure greener and healthier communities across the state. Their role is to connect people, build knowledge and best practices, advance policy, and reach all building professionals so that high-performance buildings become the norm, not the exception. Our members represent every sector in the building industry, from architects and engineers to building owners and construction professionals. You can learn more about membership, check out upcoming events, and learn how to get involved by visiting illinoisgreenalliance.org. Today's webinar is approved through AIA for one learning unit credit and can be logged for one LEAD AP or Green Associate continuing education hour. Certificates of completion for both AIA members and non-AIA members are available upon request. To request AIA CE credit or a personalized certificate of completion for architecture license CE reporting purposes, follow the QR code on your screen and complete the linked form. We will also be linking the form in the chat now and at the end of the session. For those interested in self-reporting CE hours for your LEAD AP or LEAD Green Associate credentials, we will be sharing self-reporting instructions and a fillable certificate of completion in our follow-up email to all attendees next week. And here are today's AIA learning objectives. We want to take a quick moment to thank Illinois Green's sustaining sponsors. First up, our gold and silver sponsors, with a special shout out to ComEd, USGBC, and Sloan. Also, thank you to our green and supporter level sponsors. We cannot do this work without your help. If you and your organization want to commit to advancing our vision for a net zero future in Illinois, visit our sponsorship page to start a conversation today. Now let's get started with today's program. I'd like to introduce you to our fantastic speakers, Mac and Cheyenne. Matt Carroll's enthusiasm for building enclosure work and sustainability stems from a passion for the architectural details and their larger impact on the overall building's performance. He has been working with Husarch for the past 4 years, during which he has had the opportunity to work on projects utilizing a variety of different enclosure systems. From rain screens to mass masonry to proprietary retrofit cladding system, he has seen some of the benefits and drawbacks of each. Mac hopes through knowledge sharing, the industry can begin to reckon the emissions, waste, and contamination the construction industry currently produces. Cheyenne Husar is the founder and CEO of Husarch, a woman-owned and operated Section 3 sustainability consultancy located in the Pilsen community within Chicago. Cheyenne began her career with architecture and has been constantly striving to make a larger sustainable impact by shifting from a single building focus to exploring large portfolio and system-driven projects within government and utility energy programs. She is currently the vice chair of IGA's board and is excited to connect the architectural, sustainability, and energy industries through a common goal of building efficiencies. Remember, we will have a Q&A session at the end of this program, so feel free to add your questions to the QA function at the bottom of your screen, and our speakers will address them at the end. And with that, I'll pass things off to our speakers.
Great. Thank you so much for the introduction, Ben. It's great to be here today. Let me see if I'm sharing my screen right. I think we are up here. So we might have some duplicate slides. I think we can just skip through them, but thanks for joining us today. We're going to start with a little bit of introduction about who we are. I founded the firm about 16 years ago. We've grown from that architectural focus into a team of 12. This past year, we hired our third enclosure specialist who works in forensics and restoration projects. Mac and I are both building envelope commissioning BECXP providers. And unfortunately, our third person is on maternity leave right now. So typically, I am kind of filling in at the marketing level and making everything run together. Um, but especially with her being on leave, it's been fun for me to get my fingers back into the workload. As a firm, we've always had sustainability as the heart of our work, and that kind of spreads into all the different avenues. So between architecture and building assessments, that includes accessibility, as well as kind of using the envelope to span between sustainability and into energy. So all of these things tend to work a little bit differently depending on our clients, but for us, they're all still just one massive bubble of, striving to make buildings better for, better performance and more sustainably all around. Today, we're just going to run through a little bit about this study that we've performed. We'll give you some details on what we were calling the performance, which is some hydrothermal modeling. Did I say that right, Mac?
You did.
Yes, I finally got it. And then we did some life cycle analysis studies and compared that to EPDs. And we'd like to take a look at how this all fits into that LEED v5 picture. Initially, we were thinking that this was going to be a little bit more relevant to LEED v5, but then they give us a year-long extension. So I'm not going to say that we procrastinated, but we'll get there. You guys already got to read our learning objectives. So let's get into the study. Basically, I mentioned a lot of our work, we plug in with architects and contractors. We get to see lots of different buildings and lots of different details. And it's interesting to see that nothing's really consistent. So there were a couple of cases where we started seeing an kind of a insurgence of mineral wool when we would typically see maybe a polyiso or a spray foam insulation. And when we looked into or asked the question why they were using that material instead of something like a spray foam, the response was typically either bio-based or that they were uh, more interested in looking at decarbonization. And that got us thinking, like, how does this shift performance? How does this shift kind of the overall process? What does that carbon look like? How do we make those decisions? I don't know if any of you have ever had that question of like, what's better, using a paper plate or using a dish that goes through the dishwasher? Basically, we like to have lots of those conversations in the office. We don't always get the chance to explore them though. So we submitted this proposal with the intention of being able to really drill into a problem that wasn't going to impact our clients or didn't really hold to the same requirements of our project budgets. It was also a chance to to let us explore some new software. Everybody's talking about AI, and rather than use AI on client projects, we figured why not try and test and see how those parameters work in something that's a little bit more contained. We've also got WFI modeling for a couple of projects that we were doing and wanted to have a better excuse to explore and really learn how to use that and implement it on other projects. So this conversation has basically opened a whole lot of other conversations. So this is our first time presenting this material. You'll hear us kind of say things that when we do this again, we're going to dig into and keep exploring and investigating. We also realize we're probably not the only people with these questions. So please feel free to like put your name in the chat or participate with us or join this conversation. We'd love to, like, this is a open source share here. We'll let you know of some of the limitations. And again, I did mention that that we used AI quite a bit in this study for certain things. I was unable to calculate our carbon footprint of the study, but that might be something that we get into the next time. So with that, I'm going to turn this over to Mac, who'll give you some of the details of how we started this study.
Thanks so much, Cheyenne. Yeah, so essentially, as Cheyenne has already mentioned, we've encountered a lot of different types of projects with different wall sections and constructions throughout our the work that we do, our consulting work with different project teams. In this case, we took a look at 5 different wall sections of kind of different constructions, and this sort of serves as the basis for our analysis throughout this entire presentation. So, we're looking at precast concrete, mass masonry, CMU cavity wall. That's a stone veneer wall there. We've got a brick veneer wall and then a rain screen wall as well. So kind of running the gamut of sort of the modern wall systems that are used. Yeah, and I think we've encountered all of these, and I'd be interested to hear in the chat what if anyone has worked on projects like this, and just to keep that in mind as we're moving through this presentation. The insulation that we're using is listed below. You've got the closed cell polyurethane on both the precast and mass masonry, got some polyiso on the CMU, and then a EPS and mineral wool on the steel stud and rain screen. And the R values we've got, they're pretty consistent with the code requirements for the Chicago area. The rain screen wall is a little bit higher because that project is not local. It's in a older climate. So tilt wall. Yeah. Not gonna yell things out from the chat like that again. But yeah, and we're primarily in this presentation focusing in on the insulation, but the air barriers and the other barrier systems are still pretty important as well. Could you go to the next slide, Cheyenne? Thanks. Yeah, and as mentioned, we wanted to focus in. There's so much that goes into a wall section. This presentation will, stick to a conversation around insulation and the different types of insulation and some of the pros and drawbacks of the different installations as they apply to these wall sections. So looking at the closed cell, the expanded polystyrene, and the different R values that are associated with those. So please keep that in mind. I know there's a lot of other components to the wall sections, but yeah. So moving forward into this kind of study that we did, we wanted to take our base case scenario. So what did the walls initially have, and then substitute those walls with different types of installations. So that's kind of our constant that we're switching the insulation. In order to do that, we generated a kind of matrix that looks at what actually makes sense. In most cases, I've never run into an instance where fiberglass insulation is put on the exterior of a wall. So we ruled that out for the exterior of the rain screen wall, for instance, and it just probably doesn't make a whole lot of sense to put polyiso into a cavity. So we ruled that out for the precast concrete wall. So what's remaining in the dark here, in the dark text, is kind of the scenarios that we focused in on. Go to the next slide. Yeah, so in order to kind of set the stage for the study that we did, I want to give a brief introduction to kind of a little bit of building science, not too much, but also just kind of enclosure work and how to best gauge what a good enclosure does. So in this case, control layers are super important. Yeah, sorry. Control layers are super important. We want to look at the different layers. In most modern building systems, you're looking at a couple of different layers at least. Historically, we may have been looking at a triple white masonry system that performs all of these functions, maybe not very well. Like the masonry wall may not have been an air barrier, but the modern system looks at these, and in this particular example on the left, we're looking mostly in we're looking in one dimension, and we're just kind of outlining the different layers that are important to protecting and conditioning the inside of the building. Yeah. Can you go to the next slide, please? Extrapolating that it's still pretty important. And even though our study doesn't really look at uh, the 2D analysis of these building systems, um, we still want to highlight that it's important to look at these in 2D. So one of the kind of fundamentals of enclosure work is this thing called a pencil test, and it may be performed with a physical pencil or it may be performed with a PDF markup tool. But you kind of use this pencil test to trace the control layers throughout the exterior of the building in a detail. And what this does is it ensures the continuity of these layers and can help identify thermal bridges and water infiltration and things like that. So I have a challenge for people in the chat. In this particular case, where might you see a thermal bridge based off of this pencil test in the detail? And I'll just jump to it. It's mostly you can kind of see the heat barrier, which is that insulation, but the thermal resistance of or the conductivity of the wood blocking right there is probably going to be a little bit higher than the insulation itself. Not by much, not a ton, but not as good as the insulation. So next slide. Okay, so as mentioned, there's a lot of different things that we're looking at in terms of trying to control and condition the enclosure, the interior of a building. Condensation is one of the things that plays into that in the moisture inside the wall section. So I want to start the rest of this presentation by kind of defining what that condensation is. And essentially that's when relative humidity, when the air around us or inside or outside of a building is saturated, it can no longer hold more water. So condensation happens. And that means is relative humidity, the percentages approaching 100%, about 99%. So that's kind of like one definition. Another way to think about that is the dew point temperature is equal to the air temperature. Those things mean the same thing, and this will come into play as we get further into the presentation, but it's important to keep both of those in mind. Yeah. And just to think about it a little bit more, you can think of like the colder air on a colder day. Sorry, Cheyenne. Holds less moisture. So there's probably going to be you go out on like a 50-degree day and you might see dew on on some grass after a cold day, and that's the condensation happening because the air temperature has dropped to a point, and the dew point temperature is a little bit lower as well. So thanks. So what does this kind of mean for a wall section then? Historically, we've been looking at like a steady state simulation, a dew point analysis of wall sections where the indoor and outdoor temperatures are constant. You can do a little bit more math between those. But usually you'll do a couple, one or two, maybe a handful of analyses at different indoor and outdoor temperatures. This is okay. Thanks. But it doesn't really capture the full gamut of what a wall or a building might kind of encounter in the field. In looking at these wall sections too, you can kind of see it in the way that we'd look at this. Condensation is basically the overlap of the wall section temperature kind of graph and where that overlap matches the dew point temperature. So that's kind of the indication of where condensation is going to occur in the wall. And when we're looking at that, we really want that condensation point to be happening. If it's happening at all, we want it to be happening outside of the AWB, or so that any bulk water or any water that's generated is managed by the wall system itself. So I just want to point out that for those of you familiar with the software Therm, that's a 2D software. It'll do something similar to this, but from our research, it seems like that Therm 8 might actually be starting to incorporate this next kind of system, which is the more modern standard called transient hydrothermal analysis, transient modeling, most commonly referenced by the software Woofy. And essentially what this is it's looking at, rather than those like handful of points in time, it's looking at the standard period of analysis for Woofy is a 5-year period. And it's looking at every hour within that 5-year period. And it's running the data for that 5-year period for a whole bunch of different things that are happening within the wall section. You can see here that like each of these kind of lines represents temperature and dew point temperature and relative humidity. You can and it's more commonly referenced for moisture content, which I'll talk about a little bit later as well. But go to the next slide. So this graph that is produced by the software is, you can think of it as a wall section essentially, where the left side is the outside, the right side is the inside, and then each of these layers in the woofy section corresponds to a layer in the assembly. So you've got the in this particular case, this is the precast concrete wall. You've got the concrete on the left side, and then the gypsum on the far right side. Here, I'm kind of zooming in to identify that each of these lines represents an hour in that analysis over that 5-year period. You can extend that period or shorten it. That's up to the user, but that's the typical analysis period. But I'm also pointing out how we want to be thinking about these results. So as I more or less said, we want to be looking at relative humidity, and we want to be looking at dew point temperature and temperature. In this particular case, the relative humidity is what we're looking at on this graph. And the far left is the exterior, where it looks like it's kind of approaching that 100% on the left side. But it's on the outside of the building, so it's not as much of a concern. So in order to look at kind of the critical point in this in these results, we want to be looking at closer the highest point more into the wall or on the other side of the AWB. So in this case, we look at what zoomed in, and it turns out that that's only about like 70% relative humidity. And since that's not close to 99 to 100%, we really don't need to be concerned about that. You can go to the next slide. But let's say if it was getting close to 99 or 100% relative humidity, we might take a look at this other graph, which starts to outline the dew point temperature and the temperature. And that would be for that specific timestamp, that very specific date, that very specific time that was identified to be a condensation risk. And you'd look at the kind of overlap. If that dew point temperature matched the temperature, that would be an indication that that condensation is likely to occur. Next slide. So kind of in summary with this, we're looking at steady state. It's okay for some things, especially in 2D. But transient analysis actually provides a lot more information that is important for consideration when thinking about the performance of a wall section. As we've already said, we're focusing mostly on interstitial condensation. One of the more important things to be looking at in this transient analysis is the water and moisture accumulation in materials. That can be particularly important if you have organic materials like plywood or something similar, any type of wood in your wall section, and you need to be concerned about whether there's a lot of water accumulating in that. You can look at frost and freeze thaw issues, biological and mold growth, and corrosion issues. as well, using softwares, primarily Woofy for this, but I think you can do it with some other softwares as well. So yeah, so now that we've kind of established a base of understanding for the building science and kind of the software modeling and the results, getting into what we actually did with our wall sections. We want to establish that, one, we were only looking at weather data for the city of Chicago or the Chicago weather file. We weren't looking at other places. If you tried this study in Alabama or something, you'd probably have, I don't know if probably, but you might have different results because of the higher relative humidity, the fact that it's a cooling dominated climate. It might give you some different results. In addition, um, we took the material properties that were preloaded into Woofy. We didn't really modify those too much. I think in general that's pretty accepted methodology in case unless you come across materials that aren't like preloaded into the libraries. So and the installation was only we only modified insulation in one location. So let's say a wall section had exterior insulation and cavity insulation. We really only modified the exterior insulation. We left the cavity insulation alone. So, um, so what we found after kind of going through this was that after running our baseline conditions, we actually weren't running into any issues, which is great because, as I have mentioned, these are projects we had worked on, and if the condensation, if we were finding condensation was an issue, that would be concerning. But in the example on the bottom, you're seeing that match of the dew point temperature line in the stone veneer. That's not an issue because that's happening on the other side of the AWB. But yeah, so that's kind of what we found after we ran it through all of the baseline insulation cases. And here are some of the other examples. The precast, the baseline case was with the spray foam, and same thing with the mass masonry, and the mineral wool was on the rain screen wall. So, um, interestingly, after we modified the insulations to kind of a different type, and this was surprising to us because, polyiso and mineral will have different R values than spray foam insulation and things like that. We found similar results where there actually isn't necessarily a condensation risk just by swapping out the materials or by swapping out the insulation materials. This is good information because it means that project teams can feel a little bit more free to select insulation types based on other requirements in the project, like life cycle analysis, embodied carbon, material ingredients, or cost. So that's pretty refreshing for us when we came across that. And you can see in all of these cases the temperature and the dew point temperature never match. And the rain screen wall, you're seeing kind of that like drop in the dew point temperature because of the WRB on one side and then a vapor barrier on the other. So we also wanted to take a look at the kind of critical dates that were happening where insulation, or excuse me, where condensation was happening when. So that like when we identified that particular date and hour in one of the previous slides, these are what correspond for each of the insulation examples and the wall sections. And this is something that we need to get into in the future and analyze a little bit more. But what we were finding was that most of these are happening in the late fall, or excuse me, early to mid fall. So a hypothesis is that's happening because temperature is starting to fall, and maybe the dew point temperature is being matched with that temperature a little easier than other points of the year, but we'll look into it a little bit more and report back.
I like how
So
this is also in the future, Mac. Like that was one thing I didn't pick up on. So I'm curious about like the climate data and how what their projections look like in terms of future warming, and if those data, like if we can get data samples for more like a 30 or 50-year projection or something like that. Um, but suffice it to say, there's a little bit of a crystal ball aspect to this. Um, but that brings us to kind of a life cycle analysis and carbon as we're looking at things. So I wanted to give everyone a brief overview of carbon. I feel like within this industry, we talk about carbon a lot, but sometimes it's nice to go back to the basics. So when we talk about carbon, we're actually talking about carbon dioxide. All of our equivalents, when we talk about decarbonization and things like that, use a carbon equivalency. So that accounts for all the other greenhouse gases like methane and the hydrofluorocarbons and all these like minute particles. Um, the Earth is a giant terrarium in and of itself. So there was carbon dioxide that existed. It was a basis, like a basic building block of life itself. Plants are really good at absorbing that and they hold on to it through their life and then they release it as they decompose. But it was really with the advent of the steam engine and the Industrial Revolution that humans started outpacing that natural balance cycle. And so we were able to find traces of warming back to 1830. And for those of you who've seen Al Gore's uh, documentary, or you'll be familiar with this graph, but we can see there's just been a steep incline with the industrialization of the world. Didn't mean to sound so happy about that. Um, but one of the things that I kind of wanted to think about as I understood all of this is how do we really visualize what carbon is? So it's almost like a 14-inch square section of an 8-inch concrete wall. Or you can think of it as a little kid holding a giant balloon. But basically, 1 kilogram of carbon dioxide equivalent is something that you could actually put your arms around. When we talk about a life cycle analysis, we are specifically looking at the carbon creation and from the inception of the material, whether you're mining it or whether you're recycling it or obtaining it, into how you're transforming it into the material, how it gets installed into the construction, how it's used throughout its life cycle, and then what happens as you deconstruct it and return it to waste or to recycling. I'll be honest, when we started this project, we had another person helping out with it who was kind of using AI to pull some life cycle analysis information, and they were coming up with really awesome graphics and things like that using AI. And I was really excited for this presentation. It was going to look way cooler. But then I started getting into it and realizing that it was just a lot of pretty pictures with what AI was doing. So as I started to try and use AI to develop an actual like concrete model, I downloaded like a free trial of a life cycle analysis program, and I would say it got very deep, very fast. And thankfully, with all of our lead experience, I was like, a lot of this information seems familiar from like isn't this what we look at with our EPDs? And yes, our environmental product declarations that we've been controlling or using for all of lead version 4 focuses on all of the kind of passive aspects of each individual material. So since the manufacturers don't know how you're going to actually be using this and where you'll be installing their materials, they can't foresee the the operational carbon of this. But an EPD not only looks at the carbon pieces, but all of these other influential environmental aspects. So whether we're depleting the ozone, whether we've got smog potential runoff, even if like what what's the balance of carbon or like fossil fuel usage. For the purposes of this study, we just focused in on the carbon aspects, so we could really look at those life cycle analyses. Again, we're going to be doing this again, and we're open to feedback. So if you have other ideas, please let us know. Our office runs on Google, so we were using the built-in Google Gemini. I'm happy to share this model with people afterwards. You can pick it apart. You can try and recreate your own. It was definitely a fun way to use AI without impacting any of our projects. So with that, I ended up having to build two models. I first started with a model that I said, like, create a life cycle analysis of enter in like the wall section. And every time I was running this, it was coming back with different results. So thankfully, once I got to that point, I was able to standardize the EPDs. So that I was pulling from manufacturers. I was able to cite a source. I could go back and document that, yes, these three manufacturers, and taking the average of all of them, they are all reasonable, documents that we've seen in our assessments of, regular lead projects. So then as I was running it through, the life cycle actually takes into account, of course, like the building itself, which means where it's located, what size footprint, how long it's going to be in operation, what its fuel sources are. So just to be able to get some of those numbers, I went ahead and tried to create a 60,000 square foot school here in Chicago, average 50-year life cycle. I did ask a different AI model to create an image for me, and I don't think AI has a good sense of scale because this definitely looks more like 180,000 square foot school, but I think you guys can play along with me here. So then I was finally starting to get some consistent data. I'm going to be showing you like all of these numbers. I can give the final output, which does actually have some of the EPD information in there too. Of all of these different wall sections and all of the different variations that we were looking at. So things to kind of look through as we're flipping through these are the total life cycle carbon. So this takes into account not just what the EPD looks at, but what that projected operational carbon would be. When I initially looked at this, I was really excited to see this operational carbon payback period, in 5 years and things like that. But that really only accounts for the initial life cycle, like the initial creation periods of the carbon. So in order to really be able to compare apples to apples, and especially that impact of the operation of carbon, we need to be incorporating an effective R value. We then divide that total life cycle carbon by this effective R value to get a functional carbon level. And with that, we found that actually, surprisingly, both models of our rain screens were in the top 3 with this steel stud cavity wall using polyiso, kind of somewhere in the middle. So it was somewhat unexpected to us, but I think there were a couple of things to think about. I want to go back to that visualization. If you think about what 8 million kilograms or 8,000 tons of carbon dioxide equivalent looks like, I found the image of 1,600 air balloons to be pretty useful. So if you think about how many buildings we have in operation, how many cars are being driven, maybe I need to visualize how big our actual atmosphere is, but you can definitely start to imagine and see how all of this carbon off-gassing is just like compounding and compressing within our atmosphere. So that being said, we did have a couple of limitations. So what ended up happening, if you look at our findings, our operational carbon was consistent across all models. I need to dig into that in terms of the next steps, because really what should be happening is it should be looking at the location of your finished building and taking into account where that material is manufactured. So that should vary based on whether you're in like brick country or like next to a concrete plant or just down the street from Dow Corning or something like that. There would be a variance of that transportation and distribution requirements that I would expect to see. So looking at that operational carbon payback, we found that the steel stud wall, especially the one with mineral wood, had the best payback period. And in fact, this is kind of what happens if you're only comparing carbon to carbon, you're going to be getting the you'll be looking at the material itself, not necessarily the function of that overall assembly. And so for this case, we were really interested in that assembly feature. So again, that's where the rain screen with polyiso has the lowest functional carbon. And after kind of digging into our results a little bit, we were basically like the way that we started to understand this was that the higher the effective R value of the assembly, the better the functional carbon would be. So this is why our codes are increasing the R value of our walls. But we do want to acknowledge that we know that there is a diminishing return on this, that you can only make that R value so great before the operational carbon doesn't offset the additional creation carbon or kind of manufacturing process. So maybe that's a point that we could take this to next, is seeing how this, maybe better fine-tuning where that diminishing return is. I think there's plenty of other studies that might be able to tell us that straight off the bat too. So this brings us back to what Mac was saying, that there are other considerations when we're choosing materials. In our case, at least, like insulation. There might be a cost. There could be social and equity questions. Maybe there's one subcontractor that you want to support on behalf of project diversity that works with one material or another. Even though the EPDs account for many influential factors, that one thing I wasn't seeing was like wildlife habitat. Of course, you could also be driven by political and bio-based materials. So there's still a lot of choices too. Good luck. That being said, we did want to provide a little bit of V5 context. For those of you who've been following us, we've been working on a Lead V5 blog series. Feel free to kind of see what we have so far here. It has taken a slight hiatus as they gave us the extension into next year, but we will be keeping with our regularly scheduled Lead V5 announcements. We try and do it about monthly, and we'll be updating the blog with the results from this particular study as well. As we started looking into V5, there's a major push to decarbonization. So I think that was part of what influenced this question as well. We did find 4 credits that kind of immediately speak to the carbon footprint of the materials. So both of we've got 2 within the environment or energy and atmosphere credits. We're looking at that embodied carbon within our materials, as well as that transportation demand for our location and project sites. So that being said, how do all of these concepts fit into Lead V5? How do you submit for them? We haven't completely figured that out yet. But with the digging that we've done, USGBC has us pretty well organized and summarized, like prepared with a number of kind of working spreadsheets that we can use to collect this information. If you're using AI, make sure that you're requiring your AI tool to provide your sources so you can really trace that back for yourself. So that being said, I think a lot of this conversation stemmed from the idea of building enclosure commissioning, which is an option within V5 still. They haven't made it a standard requirement, but just to help everyone understand how that's impacted. Lead V5 is utilizing some new standards. They currently require ASHRAE 90.1. If you submit your project before 2028, it'll be version 2019. After 2028, they're going to go to version 2022. So I know that's a lot of years. I can't believe 2019 is going on like 8 years ago, but besides that, standard 90.1 again, doesn't require a specific envelope or like a thorough envelope commissioning requirement, but it does require some of the air leakage tests and some of the thermal bridging and insulation requirements. This partnered with some of the ICC updates in terms of like requiring blower door testing or some of the BPI certified testing that we're seeing. Those things are going to keep growing from a performance and testing standpoint. Excuse me. There is the enhanced commissioning credit, EAC 5. You get a whopping 1 point for following the entire building enclosure commissioning. So does it really make sense for everyone to do building enclosure commissioning? Like, I think it comes down to like not trying to sell building enclosure commissioning as like it's for lead. You can get a point because that would probably be the most expensive like point you could earn. But instead, I think it's a matter of looking back on that operational version, especially if we can incorporate some of these tools with like understanding paybacks and like getting this type of information into the design side of a project and having that that lifespan information, then you can start looking at the long-term savings. And so that's going to go back to who's your client. Do they just want to get this built fastest and cheapest, or do they actually care about how they're going to be operating this in the long term, especially as energy costs keep rising and all of the great stuff that we have to look forward to in the future, which we are working to make better. So that being said, I will turn this over to questions and wanted to thank you all for being here. Mac, we forgot to update the slide with your information as well, but you guys can find us at whosarc.com, and we're happy to answer some questions right now, or you can find me later tonight at the Dirt showroom as part of the auxiliary board's conversation as well. So
Very
Ben.
good. Thank you, Cheyenne and Mac, for sharing that very informative and highly technical analysis of the building facade materials. Doesn't look like we have questions at this time, but I'll go ahead and throw a couple out there, I believe. So I'm not an architect, but I understand that the location of the air and water barrier is dictated kind of by the outside temperatures. Here in Chicago, we seem to go from extreme temperatures, hot and humid in the summer, to extreme colds and dry in the winter. And I was curious, just from typical residential stud wall construction, our air and water barrier is closer to the outside of the building. And I was wondering if that was dictated by the winter weather or the summer weather, because I imagine the condensation location is going to change depending on that outside conditions.
So within our climate, they always use the expression your weather barrier should be on the warm side. And here in Chicago, we are still technically a winter climate, so that should be on the inside of your building. So if you're in Chicago and somebody's putting their air and vapor barrier on the outside of the building, you might want to like double check that they're doing it the right way. However, as we're seeing mega insulated walls, that air and vapor barrier is changing. And we are now seeing a lot of continuous insulation exterior of that vapor barrier. So it really does depend on the details, which is part of the reason why we wanted to get into this modeling and be able to check for some of these things and understand them as we were taking on the role of consulting in those capacities.
Interesting.
And just
Yeah.
oh, I was just going to say, just to add to that, yeah, the continuous exterior insulation, if you have that paired with the cavity wall insulation and there's too much cavity wall insulation compared to the exterior continuous insulation, that'll shift the condensation point more into the wall. So where you don't really want it.
Right, right. What were some other surprising or findings that you didn't quite expect during your analysis of this stuff?
I don't know if it was, oh,
No, go ahead.
I was just going to say, I don't know if it was unexpected, but I do think this further reinforces that, like a rain screen wall is a really good wall in a lot of cases.
Could you explain to me what a rain screen wall is? I'm pretty ignorant on that one.
Sure, it's you've got in a lot of cases there'll be some type of cladding that's mounted to some structural behind it, and there'll be a gap, but that gap isn't like a brick veneer wall where, you know, most of the water is being stopped by the brick. Um, like the water will kind of more intentionally get behind it sometimes. But usually that cladding might be like a terracotta or a like a like in the case that we were showing, it was like wood slats, and there might just be a bug screen between the wood slats and the back of the
Oh,
wall, but there's still kind of like that cavity. So it's just kind of screening the rain. Um, but yeah, the veneer walls, the rain screen walls, I think seeing these results, it does kind of make sense in the sense that, at least for me personally, like a precast concrete wall, you're thinking, oh, there's a ton of concrete in that. That isn't really doing too much, but you know, the structure of the rain screen wall is um, much less massive. So
I think also to kind of add to Mac's point, then the you can almost think of a rain screen as the sump pump of building envelopes, where you're trying to control how that water is coming in and filtering out. So you're allowing that water to come in, but you have like a much more designed system to get that water out of your wall so that the
smart.
interior stays drier. Whereas if you're just using masonry or other things, there's like a mass that you're trying to that water gets absorbed, and it assumes that it can only penetrate so far into the wall, and then it will dry out as is the hope.
Yes, ideally. That's how it works.
You've got great
Um,
questions here.
I got another one for you. I understood from your presentation that you guys evaluated steel stud with various insulation types, and you found that steel stud with the mineral wool had the lowest operational carbon. I was wondering, would a wood framed wall have a higher operational carbon than steel stud?
You know, I could, within the results, I could pull that one really quickly for you. Most of our work centers on commercial work, so
Hmm.
I forget that wood studs exist.
Yeah, that's fair. Doesn't seem like we have any other questions and answers from the audience, and I am about out of my own questions. So, Twyla, anything else to wrap up today?
Yeah, thank you all for joining us. And thank you to Cheyenne and Mac for sharing your research with our audience. You'll all be receiving a follow-up email that will have a recording of this presentation and the slides as a PDF and some self-reporting instructions. And if you need to report for AIA, this is your last chance. I'm going to put that link in the chat one more time for everyone. And then we will wrap up. We're going to have a feedback survey that will open up when you close this webinar. We'd love to have your feedback on our webinar, our webinars in general. And thank you once again for joining us. Thank you, everybody.
Great, thank you all.
Thank you, Cheyenne and Mac.
Everyone,
thank you.
bye.